Okay, we're going to continue exploring this relationship between vectors and solution sets of linear equations. And this section is quite long, but what it contains is several examples of the technique that's used to write vector form of solution sets. All right, so let's see. Suppose we have the solution x1 equals minus 3, x2 equals 5, x3 equals 2. We can write that as a vector. And now we'll use column vectors in linear combinations to express all of the solutions to a linear system of equations. Remember, before we used independent variables, you know, the same thing as saying free variables and pivot variables. And now we'll use that same concept. Now we'll write those in terms of sums of vectors. Okay, so suppose we have a case where we have a system of equations, and suppose this is the RREF form. Okay. We don't have to go back to the original, just suffice it to say that when the original system of equations were produced, you got a RREF form like this. You have the two pivot variables, you've got two free variables, and you've got your constant vector. Okay, so R equals 2, the number of pivot columns. Okay, so the two dependent variables are here, and we have two free variables here. Now, when you wrote the solution vector, the way you did it was, you remember that x3 and x4 are arbitrary, and then you can solve for x1 in terms of x3 and x4, and you can solve for x2 in terms of x3 and x4. And the result is what you have here. Now, this is just what we've been talking about in the previous section. Here we have a vector, and we can break it apart depending on which parts depend on which variable. Okay, you notice that there's some constant terms. There's a 4 here, which is a constant. There's some terms that depend on x3. There's some terms that depend on x4. So you can break this up into 3 parts. Notice that only the first component has a constant 4. All the others have only variable terms. So we can associate this 4 with this vector 4, 0, 0, 0. Look for all the terms now that are associated with the variable x3. We have one in the first component, and then you have one in the second, one in the third. There's none in the fourth, but that just means that we write it as minus 3x3 minus x3, x3, and 0. Okay, x4, we do the very same thing, 2, 3, 0, 1. That gives me 2, 3, 0, 1, all having x4 as a multiple. All right, now we do the same thing that we did in the previous section, is we factor out the variable as a constant in the linear combination. So we re-express this, now it looks like a mess, but we re-express this solution as a sum of vectors, as a linear combination of vectors. Here we have a constant vector, and then here we have two vectors with coefficients. Okay. All right, so that's the procedure. Here we do a general characterization. Okay. Suppose we have a solution, and our solution is x, and we know that the form of it's good in this characterization to go back to this particular example, because they're just showing in general what they did in particular up there. Okay, so the solution is going to be x, and we know that the form of x is going to have this stuff here. Here, I got rid of the junk so that you can see it. This solution is expressed in terms of the variables x3 and x4. Right? So we know that we're going to have a solution that's expressed in terms of the variables x3 and x4. We're going to have a combination of vectors. All right, now, what do we know about the, so these vectors, let's say it this way, these vectors all have 4 components. What do we know about the last 2 components of each of these vectors? Well, we know the last component here, x4, and that's a free variable. That's a free variable, so it doesn't depend on anything. So that's going to give me simply a 1 in the x4 column vector and zeros in the other 2. Same with x3. x3 is a free variable, so these are free variables. x3 is a free variable. It's going to give me zeros in these 2 columns and a 1 here. So you can see in these last 2 components, it's going to work out. I'll have an x4 on the left, I'll have an x4 on the right. I'll have an x3 on the left, I'll have an x3 on the right. Now for x1 and x2, it's a little more complicated because in fact we don't have x1 and x2 in the expressions here. So we have to break this apart to get the vectors that we need to make a linear combination. Okay. Now here we're just systematizing what we did above. You solve for x1, and then you can rewrite this as the first component in this vector equality. Do the same thing for x2. x2 can be written as a linear combination of x3 and x4. We rewrite this as the second component of a vector equality. Okay? And this is a very nice solution form that's going to be very useful for us. All right, now notice in this case that in fact so this is our final solution form right here. Notice that as he mentions here, we don't have a unique solution. There are an infinite number of solutions, but we can easily find particular solutions simply by plugging in the values for x3 and x4 for these two vectors. So here's two different examples of particular solutions. All right, so here we'll do one more example. In this case, there are 5 equations in 7 variables, and we're given the augmented matrix. It turns out that the row-reduced form looks like this. So we can identify the free variables here, here, and here. This is going to be x3, x4, 5, 6, and x7, sorry. All right, and then the rest are going to be dependent or pivot variables. All right, so in our solution, we're going to have to write a 7-component vector, a column vector with 7 components. That's going to be x1 through x7. And we'll construct the different terms in the solution just like we did above. Of course, we're going to first focus on the free variables. Those are easy, and then we'll get the other ones later on. Now, if you actually write this solution set in the equation form, the same as we've been doing, solve the first row here for x1, solve the second row here for x2, and so on. All right? And you can see that when you have free variables, these are very easy. Okay? You can break this apart as a sum of vectors. We've done this several times, so hopefully you see how that works. Okay? And then you factor out the variables. So here we have a linear combination of vectors that gives us the solution. All right, if we do this systematically according to the procedure that he mentions, the solution, so we're going to get the same result, and we're just going to do it in a systematic way. So you have your solution vector. You know it's going to be a linear combination involving the free variables. For those entries corresponding to the free variables, we put in 1s and 0s everywhere else, so that gives us immediately this form. And you can check out that these 3 equations work. Okay. For the dependent variables, we can use the augmented matrix to get an equation expressing the dependent variable as a constant multiple plus multiples. Okay, so look at how this works out. Look at these coefficients here. How does this relate? How do these coefficients relate to the augmented matrix? That's the question. How do these coefficients in the first row relate to the first row of the augmented matrix? Let's go back and see. This one was 15 minus 2, 3 minus 9. Let's see the augmented matrix. The 15 comes from here. Then you had minus 2, 3, minus 9. Okay, so you can see that what this corresponded to was the solution of x1 in terms of the free variables, which just means you take these variables to the other side, which gives us the result. Now we can read, if we do the same procedure, we're going to be able to see immediately what we're going to do for the second row. For the second row, you're going to solve for x2. So the second row should have a minus 10, and then a 5, minus 4, 8. Okay, let's see if we're right. First one should be minus 10, then 5, minus 4, 8. All right, minus 10, 5, minus 4, 8. Right? So it looks like we're good. Okay, let's look at the x5. If we go up here, x5 should be what? here's the augmented form. All right, x5 is the one over here. x5 only has two variables, so x5 is going to be 11 and then plus 6 when we take this variable to the other side. And then we'll have x6. x6 is going to be minus 21 minus 7. So we should have 11, 6 for one of them, and minus 21 minus 7. And the 6 and the minus 7 go on the x7 column. Okay, so let's see if that works. Okay. Here's the 11, 6, and here's the minus 21 minus 7. Okay, so we do get the result that we would expect, and we notice that we simply worked off the augmented matrix. We didn't have to refer back to the original system of equations. We can read all these coefficients off from the augmented matrix. Okay. If you want a particular solution, any particular solution can be found by plugging in arbitrary values for x3, x4, and x7, as he does here. All right. Now, also, you could in particular plug in all three values equal to 0, and you'll end up with a solution. Okay. So it turns out that in this linear combination, the first vector that has no coefficient will always be a solution to the system of equations. Okay, so as he is wont to do, we're going to summarize the procedure we've talked about as a formal theorem. All right? Now, I hope you get used to this kind of way of doing things. This is kind of seems like a very ornate and King James English sort of way of expressing what we've been talking about, but it is compact and concise, and let me just help you understand how to read this. Okay, so we're talking about how to express the solution set of a system of equations expressed by augmented matrix in a systematic way. All right? So suppose that AB is the augmented matrix for a consistent linear system. Consistent, of course, means that it has at least one solution. Okay? Now, let's suppose we find a row equivalent matrix in reduced row echelon form. Okay? And it's going to have the same size as the augmented matrix, m rows, n plus 1 columns, because the constant column adds an extra column to the original coefficient matrix. Now, suppose B has R pivot columns with these indices. Okay, so don't be frightened by this. This just means that the pivot columns might not be 1, 2, 3, 4, 5. It might be 1, 2, 4, 7, 9. So here we just need to have integers indicating the different pivot columns. Okay, and n minus r non-pivot columns, these are the ones with free variables, and we specify these indices here. And we know that the last non-pivot column is going to be the last column in the augmented matrix. Okay, so let's define some vectors. This vector c, which is going to be the constant vector, these vectors uj, which will correspond to the different variables. If I go back up here, you can see how he lets c be the multiple of the constant, and these u vectors are the ones that multiply the three free variables. As you can see up here, the constant vector and the three free variable vectors. So this was u1, u2, u3, and this was the vector c. Okay, so in general, of course, we may not have three free variables. We might have more, we might have less, so that's why he's using this, these indices, these arbitrary indices. Okay, so we have one vector c, which is the constant vector. We have j vectors, which correspond to the free variables. And we can read the entries of these vectors immediately off of the entries of the row-reduced matrix B. Okay, so the entries in the constant vector are going to be 0 for those entries corresponding to the free variables. And they're going to be the entries in the last column for those variables that are pivot variables. So the vector c is obtained by looking at the entries in the last column. Okay. Now, for the entries of the other vectors, the uj vectors that multiply the free variables, as we saw before, that for the jth free variable, we put a 1 in the jth component, we put 0 in the other components, and then to get the remaining entries in that vector, you go down the column corresponding to that free variable, and you look in the row that corresponds to the entry, and you get the entry that you're going to have in this vector. Okay, so this one's a little bit harder to follow, but if you look at the particular examples, you'll see how this works. For instance, to get the look at the example here. To get this vector u1 here, minus 2, 5, 1, how did that come about from the original augmented matrix? Well, from the original row reduced matrix. Let's see how that works. Well, our three pivot variables were x1, x2, x3. So our augmented matrix was back here. I think. Where'd it go? It'll be here somewhere. All right, here it is. Let me get rid of this junk so you can see it. Okay, so remember, we're looking for the vector corresponding to the free variable x3. So here's the free variable x3. Look at this column. Look at this column here. Now, and look at the pivot variables. There's one here, 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 and I'm sorry. All right, that was right. I have the pivot variables. One is here, the x1, x2, x1, 2, 3, 4, 5, and x7. 2, minus 5, 0, 0. All right, now if you take the negatives of those, that's minus 2, 5, 0, 0. Okay, let's go back to where we're looking at now. Okay, so here is the vector that we ended up with. It's called u1, but that corresponded to the free variable x3. Look at what we have here. Minus 2 in the first row corresponding to x1, 5 in the second row corresponding to x2, and the other two free variables were, what were they? The other two free variables were x5 and x6, so we have a x5, and here we have a 0 here, and x6 we have a 0 here. All right, seems like a magic trick. Let's do that again. Let's look at u2. u2 is correspondence to the free variable x4, and we notice the entries here, minus 3, minus 4, 0, 0. 3, minus 4, 0, 0. These other entries, the 0 here, the 1 here, the 0 here, that follows from the fact that these are the entries associated with the free variables. Okay, so the pivot variables are here. Not sure if I said that right, but these are the 1, 2, 3, 4 pivot variables. These are the 1, 2, 3 free variables. So where did this 3, minus 4, 0, 0 come from? Where does that come from? Let's go back to the row reduced matrix and see. All right. Let's look at this column. Okay, it's the negative of this column. Minus 3, negated gives me 3, 4 negated gives me minus 4. This 0 negated gives me 0, this 0 negated gives me 0. That gives me all of the entries in the solution vector u4. I'm sorry, u2. Gives me all of the entries in u2. So you can try for yourself this vector u3, see if you can understand where these come from. It's going to come from a column in the row reduced matrix, and you're going to take negative of the entries. All right, so that's the theorem. That's the expression of a vector form of the solution in general notation. Okay. Now, why is this useful? Because now you have the solution specified in such a way you could program a computer to do this. You could use variables with indices, and here this tells you how to arrange your variables with indices in order to calculate the solution for an arbitrary system of linear equations. Okay, now here's the proof. This does seem very long and complicated, but what this is, and the base, what this is doing in general notation the same thing that was done in those particular examples. So you can kind of see how mathematicians operate. They do things with simple examples. That gives them the concept, that shows them how things are going to work in general, and then you have to write it in this ornate language with all these indices that expresses what you're doing in general. Okay, so I'm not going to go through the details. It is useful. I think it's difficult on a first reading, but just understand that that's what's actually going on here. Now, the rest of this section has several more examples. I could talk through these, but I suggest that you read these and work them out yourself. First of all, maybe you can try to work this out yourself before reading it and see if what you get agrees with the result. But these different examples will reinforce the same method. We're not doing anything different. We're not introducing any new material. We're simply using the same procedure in different examples. So here's one more example where he does the same thing. All right, so go through these examples. Get this down solid because it's very important. It's very key, both conceptually and computationally, for what we're going to be doing. But I'm going to end my video here. In the next video, we'll go into this homogeneous solutions, particular solutions.